So I'm Lucas. I'm an aeronautical engineer here from Brazil. I've been with Kashmir World Foundation since January this year. It's been an amazing year. I've learned, like, I can't even say how much I've learned. It's amazing. And today I'm gonna be presenting the process from going uh, from our model of Vigor Ray in OpenVSP to Rhino 7 CAD.
Right, awesome, thank you. And I think everyone knows me, but just in case you don't, I'm Aaliyah, the founder of KWF, and I love learning about new technology and working with amazing people like Lucas from around the world to help us develop technology that can basically help us protect more endangered species. Ron, you want to go next?
Yeah, hi, I'm Ron. I'm the Chief Technology Officer for Kashmir World Foundation. And well, we've been using OpenVSP for over 10 years. We love it. And but we've always been frustrated when we finally got that airplane done. It was exactly how we wanted it in OpenVSP, and then getting it into Rhino CAD always proved to be a nightmare. And we did really horrible things like just grabbing the airfoils and using a MathCAD file to recreate them in Rhino. All sorts of stuff just to try to find a way to get it done. And we got a lot of guidance from Rob McDonald this time around, and then really benefited from having one of the Rhino support staff folks, Pascal, really jump in and help out at every point of the way. And I think amazingly, what you're going to see today is what used to take us probably 4 or 5 months to do. Lucas is going to do the entire thing in under 50 minutes.
That is pretty remarkable, under 50 minutes. So I'm looking forward to that. Um, Brandon, hi.
Howdy, can you hear me okay?
Yes.
Great. So I'm Brandon Litherland, here standing in as a civilian subject matter expert on aircraft design and open vehicle sketchpad. I've been working with it since about 2014, thereabouts. So worked alongside Rob McDonald and done several of the workshops myself. So looking forward to seeing some of the problems that you had going from VSP into Rhino and either some of the successes or the steps that you've taken to try and facilitate that transition.
Awesome. Thank you and welcome. On call.
Good morning, everybody. My name is Angel. I'm a computer scientist. I'm focused on the area of computer science and AI ML, but also my background is mechanical engineering. So definitely, I'm very interested on seeing how you guys design or Lucas designed the drone in Rhino.
Thank you. Seth.
Hi, I'm Seth. I'm a fourth year aerospace engineering student at Ohio State. I just joined Kashmir Robotics as an intern in September, working on the internal components of Eagle Ray, and I'm very excited to see how Lucas did the whole transfer from OpenVSP to Rhino.
Awesome. Thanks, Seth. On.
I'm a fourth year's an aerospace
Oh,
engineering student.
on, you're kind of really low. I don't think we can hear you.
Hello?
Ah,
Hello?
much better.
All right, thank you. Uh, I'm a senior student at in majoring in aerospace engineering at University of Washington, and I joined Kashmir World Foundation and worked on the internal CAD uh, since I believe July, and I'm really excited to see what Lucas can do to sum up our work for the last few months.
Right. Awesome. Lucas, all yours.
Let's go. Um, so first of all, if you guys have any doubt along the process, don't hesitate to interrupt me so I can. Um, can you guys see my screen?
Yes.
Awesome. So we'll start in OpenVSP with our model. Here we got just the wing and the control surfaces cut out. We in this model we have everything else as well, but for the CAD process we will just be using the wing and control surfaces. So the main step for the conversion from OpenVSP to Rhino is the trimmed surfaces export. We tried a lot of other export methods, but the trimmed surfaces was the one that actually worked and was the easiest one for us. So I go with the intersect subsurfaces just to have the control surface markings as well. In the output tab, we select the step file, which for us worked better, um, unit length per meters, and a shell representation. We also tried the Brep Solid, but it didn't work so well. Wasn't that easy to change in Rhino. So I'm gonna start just exporting this surface. And then we can go to the Rhino. I just have a blank file here. I
Um,
use the, yes,
Lucas, can I just interrupt you for a second?
sure, sure.
Would it be possible for you to point to the Miro flow chart that you did just to let us
Yeah,
know where in that process you are?
sure. Can you guys see the flowchart here on the right?
Yes.
Okay. So I just did the trim surfaces export. Now I'm going to do the import with the template of large objects in millimeters for Rhino. So that's the step I'm going to do now. Just importing the file I just created from OpenVSP. It does take a while, but after that everything goes pretty fast.
So,
This is
Lucas,
the
you make it look easy, but what was like, I mean, what was the actual challenges you faced from OpenVSP to Rhino? I know it's not as easy as you make it look, so while we're waiting, maybe you could kind of like share some of those challenges.
sure. So the biggest challenge was to be able to have a closed model in Rhino. So this version is going to be the half scale. We're going to print in 3D, and so we need a very closed up model with the every surface connected, and this is because we need to shell it out to create the internal structure. So this was the biggest challenge, and that's why we went through so many iterations to see which was the right process to get to the closed surface. So yeah, I think that's it. The challenges are going to, I think I can talk about them during the process, because every step was a lot of iterations just to see each configuration and every detail to make it work. So here I'm just going to, the only thing I did different from the base file from Rhino was to name the layers here. I just like to work a lot with the layers to keep everything organized. I think it's easier. So the first thing I'm going to do is to see how long is our span, because we will be working with a half scale model and this is a full scale normally. So I'm just going to check it with the distance tool from one tip to the other. And yeah, it showed me it's the full scale span. So I'm just going to scale everything here with the automatic base point, which will be the volumetric center of the body, and I'll scale half. Um, so now I will move the body to the origin just to make things easier later in the 3-axis. And here, the way we exported from OpenVSP in the trimmed surfaces and with the subsurfaces intersected, we have the subsurfaces here. I don't know if you guys can see, but if I hide, these are our control surface markings, and those I will change the layer because we were working with them in the second part of the webinar. This first part will be just to take this exported model and turn it into something we can actually work with within Rhino. So I like to work with the shaded view just to make it easier. But now the first thing to actually work on the aircraft is to explode everything. So now we have 50 surfaces instead of one body, and we will delete half of the body. And for us to be able to actually work on the surfaces, we have to hide everything, and then we will delete the trailing edge and the tip, because those we will reconstruct later. So I can delete everything, show again. This is our half body without trailing edges. And now we move into the second section here, which will begin by rebuilding the surface. This was actually one of the key steps. We actually had the guidance from the people at Rhino. They showed us that our surface was too complicated and this make harder to work on the body. So this rebuild step is really important. We actually went through a couple of configurations here, but this is the one we found that worked well. Mainly the second and third degree for the U and V curves. And here we can see the deviation. So our file is in millimeters, so we have 0.3 millimeters of deviation with the rebuild. We can even take it down, but I don't think it's necessary. It's a very little deviation. So now we have our rebuilt surfaces. It's way cleaner, very few control points. And I will hide everything again, every surface, just to be able to delete some remaining curves. So this is the curves that have after the rebuild. So I can delete them, show the body again. This was the step we just did. And now we start matching the surface. With the rebuild and because of the little deviations, we have some surfaces that don't actually intersect or don't line up very well. So this is the step we're going to do now. I'm going to start with the trailing edge because it makes it easier later. So we are using the match surface command. And if you guys, I don't know if you guys can see it very well, but here the surface don't quite line up. There's a little step. So this is what we're going to fix now. For the trailing edge, we use tangency match, which with average surfaces and automatic as a curve direction. So now the surface should be pretty lined up, and this will make it easier later. Same thing for the top surface, and we will do this for every section and every top and bottom pair. I found that the order in which you select the edges don't influence so much. So if you select first the one going towards the tip or towards the root, it doesn't change too much. But the configuration of the match surface here, these settings, they're very important. If you change one or another, it can just create edges that are hard to be fixed later. So we've matched everything for the trailing edge. Now it shouldn't be shouldn't have any step, and the shape itself didn't change too much. We'll do the same thing for the leading edge because it's not very lined up as well. So, but this time we will use the position for continuity and the other end with tangency. The rest of the settings are the same. And we do this for every top and bottom pair of the leading edge. There we go. Now the next step is to close the trailing edge again, the one we deleted. So we will use the edge surface command. It takes two or more curves and closes it. So we'll do this for the whole trailing edge. And
Lucas,
now,
what is the width of the little closure that you created,
let me check.
or the height of it?
It's 5 millimeters.
Okay.
At the root and at the tip, it should be less. It's about 0.8 millimeters, almost 1 millimeter.
Well, it really tapers off.
Yeah. It's mainly because of the card of the airfoil, because the thickness of the airfoil is it's dependent on the card length, and so here the card is much smaller, and then the thickness as well. So now we can extend the root section just to make sure it's on a clear plane across the origin. So I will use the extend surface command and just grow it. And then to be sure I have a clear surface along the origin, I'll create a plane starting at the origin and with 1,000 millimeters size. I'll rotate it 90 degrees. So we have now a plane on the XZ plane. And we will trim our root surface with this plane. There we go. So now we're sure that the edge of the root surface is actually on the XZ plane. Then I can join every surface. And now it's the time we start checking if we don't have any remaining naked edges. So now we shouldn't have. Thankfully, we don't have it. We just have the tip, which we haven't closed, and the root, which we also haven't closed. But everything from the trailing edge and the leading edge is closed, and we have no edges remaining. Then to close the body, so we're at this step now. Sometimes, depending on the model and the configuration of every other step, we still have some naked edges, maybe at like the intersection of the trailing edge here. And then we have to go back to the match surface and then do it all over, but it should work after some time. Now we can mirror this body across the x-axis, join everything again, so we don't have the edge here in the root anymore.
Lucas, sorry, can
Yeah.
you show us again where in Miro you are in the flowchart?
Yeah, it's here.
Okay.
It's the mirror. It's just before the closed surface. Actually, now I have changed those two steps, but it doesn't matter too much because we just have the tips of the wing now open, and to close them, we can just use the command cap, and they should close with a surface here. And as you can see, we have a closed poly surface, which was our main objective. Now the whole body is waterproof, and we can use it, this closed surface, to shell out and use the internal structure. So this is the closed surface. I don't know if you guys want to kind of take a break before going to the control surface, or I can just keep going.
I'm fine with just continuing. It's only been about 20 minutes.
Okay, perfect. So this was the step that I think took us longer, going from the exported body from OpenVSP to the disclosed surface. It took us a while to just dial in which were the commands to use and what were the configurations. But with this kind of process, it worked fine. I tried it a couple of times with a couple of different configurations and it all worked. A couple of different models from OpenVSP. So to do now to cut out the control surfaces, we will start by undoing the closing we just did. So we will actually, I'll keep the closed surface. I'll just copy one and change it to the open surface here. This is the body we'll be working now, and I will explode. So now we have an open surface with every surface separated, and this will make it easier for control surface cutting. So now I can re-enable the control surface markings here, which were imported from OpenVSP, and this will serve as a guide just to cut out the control surfaces. So we're starting here. I exploded everything, and now I will start interpolating the curve on the surface. So just to be sure that these curves will be on the surface to cut out. So interp curve on surface. I'll start in the top surface, and now I have to change to ghosted view just to be able to select the edges here, and I'll do it for the top and bottom surface. With the three curves. So here's the first of the leading edge of the control surface, this side of the control surface here, there we go, and I'll do the same thing for the bottom surface. So I'll do this for the elevator, which is the one I'm working on right now, but for the other control surfaces, it should be the same. So both the aileron and the rudder, they should work the same. With the same process, you get the same results. So there we go. Now we can hide the control surface markings, and we have just the outline that we know for sure it's on the surface. Now I can hide the open surface. So here's the step I'm going to do now. It's a line in the middle of the sides. So I'll use the line command. We'll close it, both here and here. And this is the line in the middle. This will be used to create the side of the control surface later. And I will extend this line past the trailing edge to revolve later using the extend command, just selecting it and extending an arbitrary amount. There we go. So this will be revolved to serve as the sides of the control surface, but we need the revolve axis. So I'll create it now. I'll use the line command again. I'll go from this side here, and I will go perpendicular to the line I just created. And same thing for this side. And now we can already revolve the lines to make the disk. So I will select this line, use the revolve command with this axis I just created. So now we have a perpendicular disk to the side of the control surface. This was actually one of the steps we had a problem in the beginning because we were using a line in the middle of the the leading edge of the control surface to revolve the discs, and they weren't planar discs. So that was a big change we did in the middle of the process. But now we have the side discs we'll use for the sides of the control surface. And now I can delete these lines I used before just to make the file cleaner and easier to look at it. There we go. Because the next step will be the intersection between the discs and the top and bottom surface of the wing. So I'll use the intersect command, and I'll intersect the top and bottom surface of the wing and the two discs. It should create these lines for me, which will be the size of the control surface. I'll just delete the curve it created on the leading edge because it also intersected the top and bottom, but we don't need that. Now we'll extend the curves on the surface for the leading edge because sometimes it doesn't kind of touch the disc here, so we need to extend it. I'll do that for the top and bottom surface, so just select the leading edge curve and the surface, and it goes to the very ends of the surface. Same thing for the bottom here. There we go. And now just to clean out this rest we have here, we will use the connect command. So we will connect the side curve here and the leading edge curve. So now we have the curve, they are both connected. I'll do this for the other side as well and for the bottom. And this step is important that you click on the side you want to keep, because if I clicked on the other side, it would delete the part of the curve that was inside the control surface, and we don't want that. Now I can hide the discs just to make it easier to see. This is the curves we have. I can delete this one as well because we won't be using it anymore. So these are the curves, and these curves will be used to split the surface, and this will be our next step. We'll split the top surface of the wing with this curve we created. So now we have two separate surfaces. This will be the top side of the control surface later, and we'll do the same thing for the bottom here. So just selecting the surface of the wing and then the curve. Now we have the both surfaces split here. We need an offset just to be sure we have a clearance between the actual control surface and the part of the wing that is cut out for it to be able to rotate. So I'll use the command offset curve on surface. The base surface will be our top surface here, and we will offset it 0.5 millimeters just for a clearance. And I'll do the same thing for the bottom. So this is the curve we will be offsetting. I have to flip the direction. It's telling me it's going to offset it for the outside, but we want it from the inside. So there we go. Now I also move the discs inwards. So I take both discs and move 0.5 millimeters inwards just to line it up with the actual control surface side. There we go. And now I will split again this top and bottom surface of the control surface with the offset curve now. So use the split command. Split this surface with this curve. There we go. And now I can delete this intersection here, and I'll do the same thing for the bottom surface. So I want to split. Let me change the shaded. There we go. I want to split this surface with this curve here. There we go. And I can delete again. So now we're starting to see a control surface cut out with a gap here for it to move. I can also delete again the trailing edge here because we will create it again later. So now we can move to the revolve for the leading edge of the control surface. Now I'll just change these two surfaces for this layer to be easier. And now is the actual step we will do the leading edge. So I'll create some lines from the top and bottom tips of the leading edge of the control surface. So this will be a revolve curve, and we'll need to create an axis for the revolve. So we'll take from the edge of the bottom surface to the edge of the top surface here. Same thing for the other side. So from here to here, and then we can connect the middle of those two lines. So this will serve as our revolve axis. And then I can use the revolve command on this curve we just created and select the axis. So from here to here. And then we can rotate it up until we can match it here. This will serve as the actual leading edge of our control surface, but we need to split it with the ISO curve to make sure we have a smooth transition. And this we have to split with the V direction because the U direction is on the leading edge side. So with the V direction, we have a span-wise here cut. So I can cut it some distance apart from the intersection here, and same thing for the bottom. And then I will delete these two surfaces. And just to be sure we have a smooth transition between both surfaces, we use a blend surface command. So now we're here. Between this side here and the edge of the leading edge surface. We will match them for tangency. So we have a nice smooth curve here. And we will do the same thing for the bottom part. Also with tangency selected. There we go. So now we have a pretty much finished control surface, but we still need the sides. And to do the sides, we actually need to extend the surface that we just created. So some amount, both sides. And then we will trim this extended surface with the discs we have. That will be the size of the control surface. So I'll start the trim. I'll select both discs for trimming. And I'll start trimming the leading edge here that we just extended. There we go. Now our leading edge is going to end at the disk here, which will be the side of the control surface. Now the next step we have to do is to do an edge surface on the trailing edge again. It's the same command we use for the wing itself. So we can close the trailing edge here. And now we can join all the surfaces of the control surface. So it's still not a closed surface, but it's all joined up, and we will use that to trim the discs. So I just use this as the cutting object, and I'll cut the discs. So we have the sides all lined up here, and now we can join the sides with the actual control surface, and we have a closed poly surface, which was what we wanted. I'll change here, and now I can show you guys with the wing. So we have a control surface that is a closed surface. We can print it out and do the internal structure. And it's inside the wing here with a gap for rotation. And now it's actually the end of the flow chart here, but there's one additional step that we worked like kind of last minute, which is to close the wing surface so that we can have a closing here before the leading edge to house the rotation. So I'll do that right now. I can hide the open surface of the wing. I can explode the control surface again just to isolate these surfaces. I will join them, and I can do an offset surface, which is we'll use the 0.5 millimeters again, not a solid, and so it will create a concentric cylinder here with an offset. Now I can show the wing again, and it will be kind of passing the wing here, but we will trim it out to be sure it's the correct size. So I'll use the trim command, select the top surface, and then come here and trim this excess. So now it's cut out right at the surface, and I'll do the same thing for the bottom here. Select the bottom surface of the wing to cut, and then cut this. So now we have kind of the housing for the control surface, but we still need the sides of this this closing here, and then I can do that again with the edge surface command. So I just select the top and bottom here of the sides, create a surface. I'll extend this surface to go past our leading edge here. Same thing for this side. And I'll also extend this leading edge we just created. I have to explode it before. Here we go. So I can extend the surface. And surface command. So we can go past the side here we created. There we go. And I'll do this for the top and bottom sections here as well. And for this side, the same thing. With this edge again, I can go to the end here. Let me just hide this top surface, I think would be easier. So I can extend surface. And same thing for the little part here at the bottom. There we go. And now I can trim everything just to be sure we have a smooth surface. So I'll first trim the sides here with the top and bottom, with the leading edge, sorry. So I can trim here and here, which was the part we extended. And then I'll do the same thing, but using the sides as our cutting objects um, to cut the leading edge. There we go. Now I can show again the top surface, and we have a closed surface for the wing. So now the control surface can easily be housed in here, and it should be with the 0.5 millimeters clearance for the rotation. And I think that's it. That's the finished control surface cutting.
Wow, you just make it look so easy, Lucas. I think you'll be such an amazing professor when you choose to teach.
It was a lot of training involved.
You did a lot of practice on this, it shows as well.
Yeah. So if you guys have any doubts now, um, I can answer them.
Yeah, questions, comments, other ideas or anything you guys want, we could jump into a conversation.
Yeah, I just want to start off with some of mine. I don't really use Rhino all that much, but it seems a really versatile tool. So a lot of the steps that you were performing here in Rhino are, the process makes perfect sense from a CAD perspective, that you're ensuring all of your lines are well intersected, that everything is tangent smooth, has a good rotation axis so that you don't bump into yourself when you rotate. So I think that you've really captured a lot of the design intent for the control surfaces and the intersection. Um, a lot of the process here, at least the second half of it, was isolated for Rhino development of the CAD and everything. So um, my questions have more to do with on the OpenVSP side. So I noticed that you had curve adaptation tolerance set down to like 0.005 in OpenVSP. So you're getting quite a lot of points, especially along the chordwise direction down at the fuselage. And it seems like when Rhino brings that in, you're getting every single one of those nodes as either a feature line or a facet when you're going out as a step file. So part of me is wondering, did you try and use different units, like convert the OpenVSP model to millimeters and then go straight to Rhino from that format? Did you adjust any of the step tolerance to match up with the Rhino accuracy, things like that, to try and get the decimal precision of what comes out of OpenVSP into Rhino to be more aligned, to try and see if it would be happier with those surfaces?
We actually didn't try to change the step tolerance on OpenVSP, but that's a very good idea. We did change the tessellation of the wing surface in OpenVSP just to see if it kind of responded better in Rhino. But even with the small tolerance on the OpenVSP model, with the rebuild command that we used, we were able to kind of clean up all these excess points and still have a perfect surface, you know. But that's a very good idea to try to kind of eliminate a step in Rhino.
Yeah, with the trim surfaces in particular, it's using the underlying Bezier curves. So the surface representation that you see in OpenVSP with, say, your num-U or num-W settings shouldn't have any effect whatsoever on what comes out as CAD. So like num-W is 41, could be 101, it could be 17. You'll still get the same surface from trim surfaces because it's using the Bezier curves. And so that, let's see. Yeah, it looks like at least as far as the trim surfaces in OpenVSP, you adjusted the global tolerance, but I'm wondering if maybe there's something that could be done to try and clean that up a little bit as it comes from VSP to Rhino. And I think what I meant to ask, what version of OpenVSP are you using?
I think this one is the 3.27.
327.
Yeah.
Okay.
But we started the process. I think I was on the 3.26. Then we changed it, and it still worked just the same.
Yeah. So OpenVSP is up to about 331.1 right now, I think, or 330.1. And I've noticed that the trim surfaces export has gone through an iteration or so. So it might be more robust now. If you want to try a new version, that might help out a little bit.
Yeah, awesome.
Let's see. And in your global settings here in OpenVSP, can you click on the global tab there?
Yeah.
Yeah, so I noticed that when you come into Rhino, you're already trying to do that. Essentially, it's rebuilding the surfaces and trying to do effectively a cubic fit instead of using the full Bezier definition. So that's how it's rebuilding everything. Is it's defeaturing a little bit into a lower order Bezier curve, so it's easier for it to loft through. So you won't have 100, 200 points going through that. And even though that's really close, on average, you might get that 0.3 millimeter deviation. The thing that bothers me is where is that deviation? So if it's just an average where most of it is really accurate, but you have a dip somewhere on, say, the adverse pressure gradient on the upper surface, you could end up with premature separation at high angles of attack. So just because it's really good, maybe we can try and clean it up and make that zero. It'd be really nice, but yeah, but the demote surfaces to cubic button is one of those things to where you can set the cubic tolerance and you can change those full surfaces and chuck it all the way back to a cubic Bezier instead. And then at one of the points, and I'm trying to remember if it's maybe in a newer version of trim surfaces, I think there's the option to ignore the trailing edges. And so it would just leave those out and you wouldn't have to go through that step at all. Some CAD programs, being as they're kind of NURBS based as opposed to BREP solids, the direction of the curve kind of goes in a loop. And as long as it's closed, it's fine. And CAD is fine with those two passing each other and it doesn't care, but they can't handle degenerate surfaces like a trailing edge being smashed down on itself. A step file is perfectly happy with that, but Rhino, Creo, SolidWorks, any of them hate that. And so if you ignore the trailing edge surfaces completely, you might not end up with any of these gaps or issues in the first place that could save you a couple of steps.
Yeah, that's awesome because the trailing edge was actually one of the points there on the wing that we have the most trouble to kind of
Yeah.
line everything. So that's awesome. I'll try it of the new versions.
Yeah, because anything, at least from my experience, anything that can be done to isolate the primary surfaces like the lifting bodies and anything that can be as true to the original geometry as you can, then a program like OpenVSP that is using the airfoil definition and making a really smooth curve through those points to where it's effectively the most accurate representation of the airfoil. If you can avoid any type of rounding, any type of interpolation in the next step, then you're going to be much, much closer to that in the final design. And so if you can avoid things like, excuse me, CAD programs like ringing through surfaces or these little oscillations that can happen, those down the road in wind tunnel experiments or even in flight, you can see the flow pop off because of these little oscillations, and they can come back and bite you. So if you can eliminate those from the beginning of the process and move on, that more is the better, really. So if it's something that can further streamline the process of going from OpenVSP into Rhino, which it looks like it's already coming in as a really great surface, but then maybe we could avoid that in the future. But I think really you've done an excellent job.
Yeah, thank you so much. I think I'll still try to implement these changes that you've mentioned because yeah, that was one of the things that I was concerned about the rebuild because it actually just does change the surface and we don't want that from an aerodynamic point of view. So
Yeah.
I'll try to change this in OpenVSP before the export, so that we can have a more kind of right surface, the correct surface in Rhino.
Okay.
Any other questions, comments? Thank you so much for that, Brandon. All right, so if there are no other questions or comments, we're gonna call it a day and let everybody enjoy the rest of their Sunday. So appreciate you guys taking time out to be here today. And this will be recorded, so we'll definitely make it available to everyone. And then, Lucas, if you can try to work through some of the suggestions that Brandon had, what we could do, Brandon, is to reach back out to you with those changes and let you know how that transfers over based on your suggestions.
Okay. Yeah, either I saw you already posted on the OpenVSP Google group, so that's a good place, or you can reach out and send it to my personal email, and I can and do it in my off hours.
Awesome. Well, thank you so much. Appreciate it. All right, guys, have a great rest of the day and we'll be in touch later. All right. Thank you so much, Lucas. This was a exceptional presentation.